Welcome to this video. I'm going to be taking you through the AQA AS Computer Science Paper 2 in this video. So I've been asked actually quite a lot, I don't know why, particularly recently, to do walkthroughs of papers, not just for AQA but for other courses too, and GCSE papers as well. So this is the first time I've done it on my channel, so it's kind of an experiment, so you have to bear with me. So yeah, please give me any feedback if you have found this useful, or if you think I could tweak the format to make it more useful. So I'm going to be going through the specimen material as I record this. This is the first year of the AQA AS course, so this is, as far as I'm aware, the only paper available for this course. So if you haven't done it, this is probably not worth watching this video before you do it yourself, because you'll know the answers, and this might be your only chance of doing an actual AQA paper. So yes, paper 1 is much more programming based. It's still a theory paper, you still have to learn and revise for it, but this is much more your traditional sort of in the exam hall with a pen and a calculator doing these questions. So I'm going to be showing you essentially how I get to the answers. I'm doing this kind of blind. I've looked at the paper before, mainly to check that I know everything on it, or at least from the glance at it, it seemed like I did, and also to look up some stuff because different exam boards use different conventions. So I had a look at the AQA specification to see what terms they included on it and what stuff you needed to know for some of the topics. So a couple of things maybe just to point out from the from the cover. It's 1 hour 30 minutes. I have no idea how long this will take. Obviously you will see the video so you will know. 75 marks available, and you can use a calculator, so that's probably the most important detail on the front. So if we begin by answering the first question, I can't pretend to not know the first question, because this is one of the things I had to look up. So we want to okay, so our denotes a set of real numbers which include the natural numbers, the rational numbers, and the irrational numbers. So part of the course is looking at numbering systems and sets of numbers, and so the real numbers include other sets, but sort of fractions. So one example of a natural number. So this is one of the things I had to look up. A natural number is, let me zoom in. A natural number is, I guess a basic description would be a counting number. That's probably not enough if you actually had to explain it, but essentially they're naturally occurring numbers. So, if you were counting up how many people in a room, 5 people in a room, you don't say there's 2.5 people. It's either going to be 2 or 3 people, or 4 or 5 people. So that's what a counting number is. So one example of a natural number would be 2. Also it would be 5, it would be 8, it would be 50. It's probably best not to exaggerate it too much. So one of the things I looked up was there's a little bit of a dispute over whether natural numbers start counting from 0 or not. The AQA exam board say they're, that's awful. The AQA exam board say they do count starting from 0. So this is what the set of the natural numbers would be written as. So you'd write it kind of like this, and then you're not going to write all of them out because it goes from 0 to infinity. Take quite a long time. So the range would be 0 to infinity, positive infinity, and yeah, so it does start counting from 0. This is what it looks like. If you wanted to say something is an element of the natural numbers, or if you wanted to say x was an element of the natural numbers, you'd write it like that. This is called something like blackboard bold, I want to say. It doesn't really matter, but you essentially have to kind of do a bit of it looks a lot better when it's printed. You can just write a capital N, that'd probably be easier if you actually got asked, but this is going way beyond what the question is asking of us. So the next question is asking for one example of an irrational number, so the same kind of theme. So an irrational number, I guess maybe we should define what a rational number is. Or no, we'll just say, so an irrational number is a number that cannot be written as a ratio of 2 integers. So cannot. So you'll have to bear with me using a graphics tablet. It's not brilliant, and I'll probably skip bits of me writing it out instead of just an awkward silence. So in terms of what a rational number is essentially the opposite. So it can be written as a fraction. So 3/2 is a rational number. But we're looking for irrational numbers for this question. So I think the first irrational number ever discovered was √2. So √2 can't be written as 2 integers. Also, I know it's only asking for one example and you shouldn't put more than one, but another one would be pi. Pi is probably the most famous irrational number. You also have e, sometimes called the exponential number, but that's not a very good E. But anyway, so root 2 would be sufficient for that. So the second question starts off by asking us to convert a hexadecimal number into a decimal equivalent. So this should be relatively straightforward. So what the method I use to do this is kind of a table method. I think it's personally the easiest one to kind of work out what someone's doing, probably the easiest one to teach as well. So the way I'll do this, it's actually easier to convert from hexadecimal back to decimal personally, instead of the other way around. So really what we want to do, we want to write our 2 columns hexadecimal. We've only got 2 digits, so 1 and 16 is base 16 hexadecimal. This is what the subscript is meaning. So then we write in D6 here, and then what we want to do to convert from what's written in the row to what's written in to decimal, you basically multiply both. So you got to remember that D in hexadecimal is, well, firstly 0 to 9 are the same in hexadecimal than they are in decimal. So 10 then is represented by A, 11 B, 12 C, and 13 D, and then going E, F as well, up to 15. So that's because it's base 16 digits, whereas denary or decimal is base 10. So we've got to remember that D is representing 13. That's really, really tricky bit, I would say. So really what we'll be doing is 16 multiplied by D, which is represented by 13, plus 6. And if you get a calculator out to do this, you could probably do it in your head, but there you are. So the answer is 214 in base 10. So next question is asking us to represent the decimal value 9.375 as an unsigned binary fixed point number with 4 bits before and 4 bits after the binary point. Okay, without going into a massive amount of detail about binary fixed point numbers, although compared to floating point numbers they're slightly easier. So really what we're doing, we're extending the table beyond the decimal point. So we've got it's helpfully telling us to write 4 bits before and 4 bits after, so we're now dealing with binary, not hexadecimal, so it goes in powers of 2. So 4 bits before is going to be 1, 2, 4, 8. That's our column headings. Then we want to put a decimal point in here, which is how I format it. And then we're going to be, so this is multiplying by 2 each time. So this is 2 to the power 0, 2 to the power 1. Now we're going 2 to the power minus 1, which is going to be a half. And then we have a quarter. Then we have an eighth. Then we have a 16th. And this is us dividing by 2 for each column. So if we draw in the lines, yeah, not the greatest of jobs. So the way I personally convert to a binary fixed point number, by the way, it's called a binary fixed point number because this decimal point never moves. In regards to floating point, which is the other way to represent fractional numbers, the binary point, as it's now called, can move, whereas this, in fixed point representation, the binary point is fixed in this position. So actually, I have missing a column here. So this hasn't got a heading. There we are. Okay. So I'm going to write in, oh no, we need to find 9 in binary, and then we need to find 0.375 in binary. So I separate the integer part and the fractional part. So 9 in binary is going to be, the way we do this, we go, how many times does 8 go into 9? It goes in once, remainder 1. And so 4 doesn't go into 1, neither does 2, but 1 goes into 1. So this is the binary equivalent of 9. And so this bit's done, the other side of the binary point, so we need to represent 0.375. So I guess the first thing you can do, you can go, how many times does a half go into 0.375? So bearing in mind this is 0.5, it doesn't go in, but a quarter does go in, so 0.25 does go in. So actually we can break this up into 0.25 plus 0.125, and 0.125 is the same as an eighth. So we don't even need to bother with a 16th because we can write a 0 here because we know we've got 1 quarter and we've got an eighth, and so we can just write 1, 1 here and 0 here. So this is our unsigned binary fixed point number of the decimal value 9.375. Right, next question. So asking us to represent the decimal value minus 67 using 2's complement, so representing it as an 8-bit 2's complement binary integer. So 2's complement is a way to represent a signed signed number, so I don't think you need to know of any other methods to do this. So 2's complement, there's a couple of ways you can actually get 2's complement. The first thing I always would want to do is work out what the positive 67 is, and the positive representation in 2's complement is the same as the unsigned representation. So if we work out what 67 is using the same kind of methods, so it's 8 bits, so it's going to be 128, 64, 32, 16, 8, 4, 2, 1. That's our column headings, and we draw our lines in. Acrobat's taking ages with this. So we're trying to represent 67 here, plus 67. And technically the far left bit, which is called the most significant bit, this is the least significant bit. This is technically now a sign bit. So a sign bit means when it's 0, it's going to be positive, and when it's 1, it means negative. So sign 0 is positive, 1 is negative. And that's relatively important, you'd say. So technically our most significant bit is now talking about the sign of the number, but doesn't really matter for our purposes. So 67 doesn't, so 128 doesn't go into 67, so it's going to be 0 anyway. 64 does go into 67, so we have a remainder of 3. So we can do zeros in all of these, and then 2 goes into 3, remainder 1. Oh, no, 2 goes into 3 once, remainder 1, and then 1 goes into 1. So this is us representing positive 67. And so to then convert to negative 67 using 2's complement, one method you could do is do 1's complement, which is inverting all the bits, so you flip the bits, then add 1 to it. The quickest method to do this, I think, is to use, this hasn't really got a name, but if we write down what positive 67 is, so it's going to be 0, 1, 0, 0, 0, 0, 1, 1, what I've done up here. So negative 67, the way you do this is you start copying from right to left, and until you copy a 1, you just you then, so after you copy a 1, you start flipping all the other bits. So let's do this in action. So say we had leading zeros here, we'd copy them, but we've got a 1 here, so you write a 1 down, and then we've copied a 1, and then we start flipping all the other bits like this. So this is actually our, this is our 2's complement binary representation. So it's very, very simple. As I say, all you do is copy from right to left of your positive representation, and then until you copy a 1, so you write 1 down, and then you flip all the other bits. If I show you maybe worthwhile how you then convert from 2's complement to decimal, that might be worthwhile. So I almost use 2 different methods depending on which conversion we're doing. I use this method when we're going from decimal to binary, but if we're going from binary to decimal, I use a different method. So this is using a negative most significant bit. So instead of 128, it goes negative 128, and you can use this method to convert to 2's complement from decimal, but I find it personally not as easy as this. But to convert backwards, it's really useful. So this is then 64, 32, 16, 8, 4, 2, 1. By the way, this has got nothing to do with the question, I'm just showing you this because you might get the reverse in your actual exam. So we write a number in, so say we're given this number, we want to find out what it represents in decimal. We are going to write it in when it lets me, 0, 1, and so we basically use the same method we use for hexadecimal. So we multiply up from the row to the column. So we go, we've got 1 times a negative 128 plus 32 plus 16 plus 8 plus 4 plus 1, and then this, I'm going to trust, adds up to negative 67. And so you can either think of the most significant bit as a negative value, so negative 128 if we're using a byte, or you can think of it as the sign bit, depending on what method you're using. Okay, so the next question is asking us to add up 2 binary numbers. Okay, so we need to perform binary addition. So it's asking us to do it with 2's complement numbers. It's actually the same process. It's not any different to if it was any other binary number. So I'm actually going to write it out here because it will be, I can do it slightly bigger then. Okay, so this is how you lay it out if you want to do binary addition. There's a couple of rules for binary addition. When you are doing 0 plus 1 or vice versa, this is going to give us 1. 0 plus 0 is going to be 0. 1 plus 1 is going to be 0, carry a 1. So this is introducing the concept of carrying, like we have in normal sort of addition. And if you have 3 1s stacked on top of each other, this leaves 1, you write down 1, and then you carry a 1 2. So I don't think we're going to come across here, it doesn't look like we are, but this is the kind of 4 rules we have. So if we add it together, so 0 plus 1 is 1, 0 plus 1 is 1, 0 plus 0 is 0, we have 1 here, 0, 1, and now we have a bit of a, we can actually use one of our rules. So 1 plus 1, what we do, we write down a 0, as I've said, and we carry a 1. So I tend to write it up here, you could write it down here if you wanted. So 1 on its own is like this. So I know exactly what the next question is going to be. It's so predictable because we're dealing with 2's complement and we've had an overflow into our sign bit. We know exactly what this question is going to be. It's going to be asking us, what problem has occurred from performing the calculation using 8-bit 2's complement binary. So the answer is, and this is going to be a relatively, it's only worth 1 mark. Okay, so it's not, I was going to prepare to do a bit of a long answer. So basically the idea is that the two numbers are too large to be stored in 8 bits 2's complement binary because it's overflowed into the sign bit. So now we've got 2 positive numbers and it's become a negative number. So let me just write this up. So I'll read it out for you in case you can't read it, which would be understandable. So I've written the numbers are too large to be stored in 8 bits as a carry is overflowed into the sign bit, making the result negative. So the key word here is really overflow. This is what an overflow is, in case you get asked. So moving on, that's the end of question 2. So question 3 starts off by asking us about ASCII. So, okay, explain what's meant by character code. Right, so a character code is a binary representation of a character. So it's saying like A is represented by this binary number. So it's a binary representation of a character. Okay, so the next question is asking us to complete table 1 to show how the word B would be encoded in the binary form of ASCII. Okay, so we're going to have to use this information for A equals this. So the way it works in ASCII is the character codes, they're all lined up. I guess the word would be simultaneously, as in A, B is going to be the number after A, and then C will be after B. So this is, we need to use this information. So this binary number, B is going to be 1 larger than A, and then C is going to be 2 larger. And so if we just deal with E in a second, so B is going to be 1 larger than this, so it's going to do binary addition again. Plus 1, and so we have our carry, and then 1, and we should write it out like this. So this is what B is going to be because it's 1 greater than A. So maybe we just do it on the side, but A to B is 1, so plus 1. A to E is going to be, so we've got B, C, D in between, so this is 1, 2, 3, 4, so this is going to be plus 4. So we need to put plus 4 on instead, so let's do it in blue. So again we write out A, we could just do plus 3 with B, but you might have made a mistake, so it's worth doing this. So for me to write out 4 in binary, and 4 in binary is just going to be this, because this is the 4's column, this is the 2's column, this is the 1's column, it's got 1, 4, that's 4 in binary, and so we need to add this up, so 1, 0, 1, 0, 0, 1, 1, and so this is our representation of E. Right. A program has been developed to convert a string so all its characters are in uppercase. The program does this by taking each character's ASCII binary code and applying a bitwise AND operation to it using the mask this. Okay, right, so a bitwise operation is an operation that, how would you describe it, occurs, it performs it on individual bits, or in this case we're using AND, so it's going to be pairs of bits. So so it deals with pairs of bits as opposed to a whole set of bits. So a mask is something that can be used to keep certain bits of a number, a binary number, and ignore or mask out other bits. So the way we'd find... Okay, I better read the question. So it says convert the lowercase character c, ASCII code this, into the uppercase character c, using the method described above. Okay, so the way we're going to do this is firstly I'm going to write down lowercase c. And basically the mask is going to be used to perform the AND operation, because we need another number to actually perform it. So I'm going to line it up like this, if I can. So I'm going to line it up a bit like I would with addition, but I'm just going to write AND here so we can make sure we know what we're doing. And basically, instead of looking at it as a whole, we're looking at it in terms of the individual bits. So first of all, we want to say and 1 and 1 is going to be 1. 1 and 1 is going to be 1. 0 and 1 is 0, just using the properties of the AND operation. 0 and 1 is going to be 0, because for AND to be 1, if it's the only way it's going to equal 1 is if you have 1 and 1. So 0 and 1 is going to be 0, 1 and 0 is going to be 0, and 1 and 1 is going to be 1. So this is our uppercase C. Okay, so next question, let me zoom out, it's got a bit of a big diagram. Okay, wireless networks make use of a carrier sense multiple access and collision avoidance method. Okay, so this is a protocol you need to know about when accessing a wireless network to transmit data. So we're talking about wireless networks here, maybe that's worth underlining. So, simplified state transition diagram of this protocol without use of request to send. Okay, so that's good. Essentially, this request to send, clear to send is kind of like an add-on to this protocol, but it not being here is going to make things a bit easier for us. So, complete table 2 by writing in the descriptions that should appear at positions 1 to 4 in figure 1. Okay, okay, so we need to basically fill in the gaps. So let me just try and work out what's going on here. So this is the data waiting to be sent, so the wireless device is sensing. So maybe I should talk about a bit about how this protocol works. So really it's a protocol to avoid data collision, or try and prevent it as much as possible. So really what's happening is a wireless device will have data to send, it's going to transmit to another wireless device, and first thing it will do, it will check the transmission channel is clear. So it will check that no other device is broadcasting at that time, transmitting data. If it's not clear, it will wait a random amount of time. And I think random is a key word here. So the reason it's random is if two devices are transmit at the same time and they both realise that actually the channel isn't clear, if they both waited, say, 5 seconds, it's just going to be a recurring cycle of them transmitting at the same time. So if it's random, it's meant to avoid this issue. And so when data is sent and it's received, you get something called an acknowledgement sent back from the receiving device to the sending device, basically just to say that the data's got there without being corrupted. And if you don't get that back, you have to wait again a random amount of time. And I imagine this is what's happening. Let me just have a little think about it. So this is the wireless device sensing. So I'm guessing this is the device checking the transmission medium is clear. And so I'm guessing it's assuming that it is clear, and so one would be it would go to the transmitting stage if the channel was clear. So I reckon 1 is going to be channel clear, and so when it transmits, the wireless device becomes idle. So the wireless device, I'm guessing, is the transmitting device in this case, so it'll become idle until it has more data to be sent. So I guess this is kind of the end of the single transmission, and so the reason it would end if it gets this acknowledgement back. And so I guess this leaves us, yeah, this fits in quite well actually. If it didn't get the acknowledgement, so no, I'm going to have to write it out below, and then we're going to have to wait a random amount of time. So let's write this in, and this is basically something you just have to learn. the key word is really random and acknowledgement, and perhaps channel clear as well. So let's write this in. And the final one is wait for a random amount of time. So random, like I say, is really the key word. Okay, again, apologies for the handwriting. It's not actually this bad in real life, but graphics tablet makes it 10 times worse. Okay, so I reckon this is just filling in the blanks for this diagram. Okay, so how many more bits have we got for this question? Just this? Yes, we've got 2 more parts. First one is about SSIDs, so service set identifiers, and again we're talking about wireless networking still. So an SSID is kind of like a network name. Again, that's kind of a basic description of them. So, you know, when you connect to Wi-Fi, you list the networks in your vicinity when you know, on your phone or on a computer, and it's the network name, so it might be the name of your household, whatever. And so it's asking why some network administrators turn off SSID broadcasting. Okay, so this is about security, and actually okay, so let's firstly explain what this does. So it's the name of a network. So I've written there, the SSID of a wireless network is the name that identifies it. So the role of it is basically to connect to a network. Your device has to have the same SSID, I guess you'd say, programmed into it or stored into it to connect to the network sort of automatically. So when you select that box that says connect to the network automatically, your device is saving the SSID, and to get the SSID, it's publicly broadcast. So let's write programmed in it or into it. So talking about why some administrators might turn it off. So I guess this is what would get us our 3rd mark, hopefully. It's seen by some as not a good thing security-wise. I was kind of under the impression that it was a bit of a myth that the SSID was a security issue, because actually it makes little difference. But AQA obviously are not under that; they don't have that information. So, I guess it means if it's broadcast. So this is the fact that it's being sent out by the device. So if it's being broadcast, okay, this is the first question I've really sort of had to think about slightly more. I don't know, it caught me by surprise a little bit. So what I've written is the SSID of a wireless network is a name that identifies it. So that's our sort of just a little bit of a definition. And then its role is that for devices to connect to the network, the device must have the network's SSID programmed into it, full stop. If it is being broadcast publicly, anyone can join the network, assuming there's no other security. So there should be other security. Again, this is what I'm struggling with a little bit. So some people see public SSIDs as a security issue, so hopefully that will get us the marks, although it took me a while to get there. Okay, so explain why browsing the internet might be slower at a public hotspot in a coffee shop than at home on a wireless network. Right, so coffee shop is likely to be very busy. So yeah, let's write that. So it's only 2 marks, so I'm going to try and put down 2 reasons. So the first reason might be, a busy coffee shop might have lots of devices trying to. Let me think of a way to write this. Okay, again, the handwriting is just atrocious, so apologies. What I've written is a busy coffee shop might have many devices connecting to the same access point, so that's maybe a key term. I've no idea if it's on the mark scheme or not, but an access point is, so it could be like a router. And so depending on what access point they have, if they have like an industrial one, it could handle hundreds of clients. But if it's just a normal one, like one at home, it probably wouldn't be able to handle the client load. So A second reason might be kind of on the same theme about data collisions. I mean, this might get us 2 marks. I kind of doubt it. It's kind of a weak answer, if I'm honest. I'll see if I can think of a better one. But another one might be data collision. So we talked about the carrier sense protocol, which is designed to avoid data collisions. Well, if data collisions still do occur, and so data collisions might occur because of lots of devices transmitting. Right, so I've written data collisions will be more likely to occur. And a data collision is when data becomes corrupted because, I mean, you can think of it as colliding, and so it needs to be retransmitted because of the protocol we just looked at. And needs to be retransmitted. So you can imagine how that would slow the speed down if you're browsing over Wi-Fi. Okay, hopefully that'll get us 2 marks. Okay, question 5. So let me zoom out. The OpenSSL product is a collaborative effort to develop a general-purpose cryptography software library for encrypting data transmissions. In April 2014, a bug known as the Heartbeat bug was found in the OpenSSL software library. The bug allowed anyone on the internet to access the memory of systems protected by vulnerable versions of this software. According to web server statistics, the bug could have affected around 60% of known web servers. Okay, first question is what is encryption? So not massively to do with that, but encryption is the process of making data secret so that only the authorized intended viewers can understand the message. So I guess the point of encryption isn't to stop people intercepting the data, it's to stop them understanding it if they do intercept it. So let me write this up. Right, so I've written it's a process of making data secret so that only the authorized viewers can decrypt and read the data, and third parties cannot. So third parties are people intercepting the data. So really the process of encryption is going from something called plain text to ciphertext. And ciphertext is basically unreadable, an unreadable message. So plain text is just your normal written message, and it's scrambled up by a encryption algorithm, and it becomes ciphertext, which can't be read. And then you decrypt it by knowing the process that the algorithm has done, and then you can read the data. It goes back to plain text. Okay, so the next question is not massively to do with encryption, it seems. It's an example of open source software. Okay, so open source software is where the source code is publicly available, so probably Linux is the best example. And yes, the source code is freely available for inspection. And so describe 2 benefits of having the source code of software publicly available. Right. The key word I've noticed here is inspection. So that kind of implies someone's looking at it within quite a lot of scrutiny. Like there are quite a few reasons why it's good publicly available, but inspection implies people are looking for things, and so you can kind of guess what the answer is going to be. So when you have software openly available, when people can see the source code, they can test it for errors, and so lots of people can use it, lots of people can test it for errors. The testing budget of a small development team probably wouldn't allow them to do massive amounts of testing, whereas if it's publicly available, lots of people can test it in theory. So let's write that up. So code will be tested and checked for errors in more detail, and so errors can be fixed quickly. If people have access to the source code, that is the code written on the screen, they can try and fix errors for themselves. And actually, I guess the idea is in this case study that the Heartbeat bug was found by someone inspecting the source code. Okay, a second reason might be that, again, on a similar theme, for security can be examined and, I guess, again, tested, but we don't really want to say that again. So let's say verified. So the security can be verified on a greater scale. It's not the greatest verified. Not the greatest argument, because actually some people could, say that actually can be verified on a greater level, a greater scale. Because if people have access to the source code, if there is a security issue, it can be sort of infiltrated a lot easier. So I said also that people might be looking for flaws / holes. But like I say, this could be seen, so potentially in your exam you could have the opposite question: what would be a drawback of having the source code of software publicly available, perhaps in the context of security? And you could say that actually, if there is a security bug, people can see the code, they know how to exploit it, and it could be a major issue. Okay, so the third part of the fifth question, this bug was introduced into the code on December 31st, 2011, but was only discovered in 2014, so later. State one reason why the bug took over 2 years to find. Okay, it's only 1 mark. Let me have a think. So I guess there's probably loads of reasons why. Perhaps. Okay, the first one that I thought of, I'll be honest and say, that was probably because this is probably one line of code within, hundreds of thousands potentially. So, okay, let's say, it seems a little bit, I don't know, weak, but the code is very long and complicated, and so it probably wasn't obvious. Writing that, I've actually thought of maybe a better answer. It might be better to say that actually, and it kind of leads on for this not being obvious, was the fact that actually it didn't have an effect. It wasn't like it was causing the software not to work. It was just a bug that didn't really affect the running. So no one noticed it because it wasn't actually affecting the overall running of the software. But I'm not going to write that because it's only 1 mark. Okay, so moving on. Government agencies sometimes require that they're given copies of encryption keys. Okay, that's quite a contentious issue. This allows these agencies to decrypt messages encrypted with these keys. So state one reason for and one reason against the government having the ability to decrypt any encrypted messages. This has been in the news recently. I think Apple have refused to give the FBI access to some terrorists' data stored on their iPhones. So reason for a reason for the government having the ability to do this. Well, the main reason is to prevent crime. So, yeah. So I've written so they can detect and prosecute illegal activity. Often, certain sections of the internet, so like the parts of the deep web, there's lots of people, use it for illegal activity, and people message, other people doing crimes. So a reason against would be, how would you phrase that? I guess sort of a personal privacy argument. So yeah, it could be viewed as an invasion of privacy. There's not really a best way to describe that, unfortunately. Right. Okay, what is meant by the term stored program concept? So this is the idea that data and instructions are stored in the main memory, so the RAM. So memory equals the RAM. And then when the processor needs the data stored and the instructions stored in memory, they can then be fetched and executed by the processor. So let's write this. Okay, so basically I just wrote what I said, except I added in the decoded stage because I've just looked at the question below. So the next question is a 6 marker, so that's always fun. And it's asking us to describe using full sentences the steps involved in the fetch execute cycle and how these registers here above are used. So what I was thinking as I was writing that is to pause, and I'm going to write in what these registers do. Okay, so I guess I should probably explain what a register is. I wouldn't actually do this in the exam. I'm more doing this just in case you didn't know. So a register. I might jot down a couple of them just so I didn't forget. But it's just a register is a small section of memory in a processor. In fact, it's probably better to say storage instead of memory. Okay, so the current instruction register stores instructions that are currently being executed. That one you could probably guess. The memory address register, again, you can probably guess, holds the memory location of the data used, of the data being used or written at the moment. And the memory buffer register is what holds the actual data being read or about to be written to memory. The program counter stores the memory location of the next instruction needed, so it increments by updating it itself. The status register contains data about the current state of the processor. So what I would do here, and I'm going to do quite an extensive plan, and then I'm probably going to type it up without having you watch it. So I always do a tiny bit of a plan, but I'm going to exaggerate it a little bit. So we fetch, decode, execute cycles. We need to write about each one. We need to try and involve as many of these registers as possible. So the fetch bit starts off with the first one of the the program counter is holding the instruction. So the program counter holds the address of the next instruction, and then this is transferred to the MAR, which as you can see is the memory address register. So this address is transferred to this register, which is holding the current kind of address to be fetched the data from. So I guess the next step would be so the address is going to be sent. You can see me having to think about this. This isn't something I just remember. The address has to be sent via something called the address bus. To main memory. So the address has been sent to memory. The memory then sends back the data or the instruction at this location. So sent back via the data bus to the memory MBR, and then sent back via the data bus to the memory buffer register, and then this is sent to the current instruction register. And the final stage of a fetch cycle is to increment the program counter. So this is kind of the term we use, but really we're just saying to update it with the next instruction. So the fetch stage is definitely the most you're going to write about. The decoding stage is really just to understand what the instruction we've got currently stored in the current instruction register means. So really the only step of the decoding stage is the instruction is split up into its components, so that's the opcode and the operand. So the execute stage is really just working out what the actual instruction is, so looking it up in the instruction set. The instruction set of a processor is all the instructions it can carry out, and it kind of, obviously it's not actually like this, but you can think of it as the kind of additional information surrounding each instruction. And then depending on what is happening, it might be sent to the ALU unit or other parts of a processor to actually get our result. Right, because this looks awful, I'm going to write this up, probably type it up, so I'm going to do that now. Okay, so like I said, I've just written up basically the same thing as I did above in planning, and as I said, I wouldn't actually plan in the detail I just did. I do a couple of notes jotted down, especially if I don't want to forget something, or and if I had a mind blank at this stage when I saw this question, I completely forgot what the registers did. Usually I then leave the question and come back to it at the end. And some exams I I'll only do half the questions first time because I just leave them to the end and go back and do them again. So that's my sort of technique. But you can read this. I haven't read it through. I tried to do it in kind of exam conditions. It only took me sort of 3 or 4 minutes. So yeah, I wouldn't do a plan in this amount of detail. This is more just hopefully show you my train of thought. Sorry about that, just had to restart my Adobe Acrobat, which was a bit strange. Anyway, so we need to explain the term low-level language, and so this kind of comes into assembly languages and just machine code, which is sort of just zeros and ones, and machine. And the idea of low-level languages is they have a low-level abstraction, whereas high-level refers to the fact they have a high level of abstraction. It's not like, a common mistake is that a low-level language is kind of like low ability, and high-level is, kind of an intellectual language. That's not the case. We're talking about low level of abstraction. I guess the definition I'd give is it's only worth 1 mark. The code is I'm gonna say the code is very similar to the processor instruction set. I'm just replacing it with the language has instructions very similar to a processor instruction set, because code on its own might not be sufficient. Okay, next question. Using the assembly language, so okay, that's what I meant by when I said assembly. Instruction CMP R2 R3 explain the term opcode. Right. Again, only worth 1 mark. Quite a few lines though. When it's assembly languages, it looks like this. These are talking about registers, so these are the operands, these are registers, and I happen to know that this is compare. If you didn't recognise this, I mean, this is relatively easy to work out, but if you didn't recognise it, I wouldn't imagine you need to know what that is to explain this term. So this is using it. So I'm going to write. The opcode is the I guess representation of the actual instruction, which in this case is compare. Okay, that's a slightly weird question. Right. Okay. Oh, okay, blimey, we've got a whole table of instructions in assembly code. Right, okay. Is compare on here? No. Okay, fine. Right, so we're going to have to use those, are we? Okay, first question is, explain what immediate addressing is and write an example for use of the MOV assembly language instruction from table 3 that uses immediate addressing. Okay, so the MOV is going to be move, presumably. Right, okay, so it's immediate addressing because you're going to copy an actual value, are you? Yeah, okay. What else does it say? So, operand 2 can be interpreted in 2 different ways depending on whether the first symbol is a this is what we want. I'm going to call it a hashtag, or just a hash symbol, hash character. This is going to use the decimal value specified, so it's not it's not an address anymore. It's going to become the actual literal value of 25, which is what immediate addressing is. And so yeah, this is the register. And what else is important? The available general purpose registers that the programmer can use are numbered 0 to 12. Okay, I reckon that's going to be important. Let's just highlight that for now. That might mean we can't go beyond 12, but that might not be much to do with it. Okay, so explain what immediate addressing is. So immediate addressing is when data is loaded sort of directly. So the idea is nothing is actually sort of fetched from the memory. So I guess the textbook definition of immediate addressing would be that the data, the operand is part of the instruction, and okay, so it's only 2 marks, and we need to write an example, so I don't want to forget that. So let's just say that the data and so is loaded directly. So I want an example with move. So let's just go back and look at what it was. So move register, and then we write our hashtag number. Okay, so let's do a proper example. Let's just actually write in numbers. So we need MOV, then we write our register number. So it turns out it does come in handy. I'm glad I spotted that, because it's got to be between 0 and 12, our register number. So if we did 13, I don't know if you'd use a mark for it, but it's not in this example. So let's do register 6, and then we do a comma, and then we're going to do our hashtag and just any number, I suppose. Let's just do 9. So this is saying we need to move 9 to this register, but instead of this being an address to somewhere in memory, this is going direct to the register. So it forms part of the instruction as opposed to sort of two separate parts. That's sort of a textbook definition of it. Right, so figure 2 shows a block of program code written in a high-level language. So this is a high level of abstraction, so it's very different. This is very different to the, not only different to the assembly language, but different to the machine code, obviously. So write a sequence of assembly language instructions. Okay, that sounds... Okay, then that would perform the same operations as this code. Right, assume the register R1 currently stores the value associated with X, register R2 stores the value currently associated with B, and that R3 is available if needed. Right. Okay, so let's work out what this code does. So it's going if X equals 5. So we're doing a comparison here, aren't we? So let's just write compare. We might have to use the CMP we looked at a couple of minutes ago. Then, so if it does equal 5, then B is assigned 10. So this is us comparing just with one equal sign, and this is assigning 10 to the variable B. So if X is not equal 5, it's just going to go straight to the end. So this won't be executed. So what I'm going to do, I'm going to open up the instruction set on a different screen. Right, so it turns out compare is actually on that instruction set, despite me saying it wasn't. So that's just me not seeing it properly. So what we want to do, I guess our first line is going to be the same as this line, so we are going to use compare, I think. So let's write CMP. So register 1 is, it says currently stores a value associated with X, so yeah, we want register 1, comma, again it's very similar to above, the immediate addressing 5, apologies for that hashtag. So the next line we want is, so the next line written, so I'm going to write the line for this code, although we might change my mind in a minute. So we want to move 10 to B. So R2 is associated with B, and we want to move 10 here. But we've got a condition here. We've got, this is our conditional, and if it's not, so what it's doing here, it's comparing them, and then it's going to execute this line too. We don't really want that. We want this only to be executed if this is not. We only want this to be executed if this is true. If this is not true, we want this line to be skipped. So we're missing a line here, I reckon, or at least 2 lines. So what else is here? So actually this must be it, because we've got branches. We're doing with conditional statements, so we want to branch to a different instruction. So it's going to be one of these. So we write B, and then we have several different conditions. So we want to branch to the end away from that line about moving when it's not equal to. We don't need to write equal to, because it's going to be the next line anyway. So we can write, so our instruction, hopefully I'm explaining this okay. We want to write B, NE, then we want a label to branch to, and the way you write it is, you write it like you write the line of code and then you put the label at the bottom. So I reckon I'm gonna change my mind and I'm gonna move this. So instead I'm going to write BNE, which is standing for branch not equal to. Then I'm going to do a label. So my label is going to be, I guess we can just write it same as end if. So it tends to be lowercase and together. So we'll just write end if, that's our label. And so this is our branch condition, and we want to write label. So same label. And basically this is going to branch to this label if it's not equal to the statement above. So we can then write in the line we just got rid of. So yeah, I think this is going to work. This is just going to replicate the same one as above. So it's firstly going to compare whether 5 is in register R1, and then if it's not equal to this, if this is not true, it's going to branch back to our label. So this is the idea of the label. Oh, that's the wrong place. Like that. So we have 2 labels and it's going to branch there. So that's this question, I think. Relatively easy, 4 marks, hopefully. Okay, this is a new recording now. I was recording that the first part of this video quite late at night, or I guess early in the morning, so I was losing the will to live a little bit. You can hear my voice, so now I need to finish the paper. So we're resuming with question 7. So this is a long 9 marker, and this is probably going to be the largest, or I should say the longest answer in the paper. So let me get a highlighter out. So a well-established use of robots in industry is the spraying of car bodies on a car production line. A robotics researcher is investigating the feasibility of developing and installing in a car a computer-based control system to take over completely the driving of a car on public highways. Okay, so this is talking about automation, which is creating and designing computer models of real-life systems. Okay, so she has identified some sources of input into the control system already. So listed are high resolution video camera, stereoscopic digital camera, not totally sure what that is if I'm honest, a long range radar, short range radar, GPS receiver, and outputs, position of steering wheel, and forces on the pedals. And so the question is, a very long question, discuss why automated car control is a harder programming problem to solve than developing programmed control of a robot for spraying car bodies on a car production line. So I guess this is going to be part 1 of the question. So I guess doing a bit of exam technique, when you see a discuss question, this is really presenting key points. So for this part, we need to essentially come up with some key points for why it's going to be harder to program a car than it is to program a robot for spraying paint on cars. So the second part of the question is about what processing input data will be necessary and why. So the why is quite important there, to obtain sufficient information to safely and reliably control the driving of a car by a computer. So now we're focusing totally on the automated car, and including your discretion the source of input you've used and the information derived from it by processing. So I imagine to get 4 marks in this question, you'll need to talk about both. So you'll probably need to talk more about the inputs from this point, because it's listed quite a lot of inputs. You haven't really got any excuse for not knowing any of them. So let me do a bit of a plan. Right, so cars v robots, like something out of a movie. So this is for the first part of the question. I know technically they're both kind of robots, but so the first thing that's going to be, I guess, clear is that the robots spraying paint are going to be in a very controlled environment. It's not going to be a changing environment, whereas cars are on a road. It's very unpredictable. Human behaviour is unpredictable. They might be, driving alongside other automated cars, but also cars driven by humans. So it's much more unpredictable. So yeah, cars are going to be very in a very unpredictable environment, so they've got to react quickly, and obviously cars are going to be dealing with human lives, whereas robots, if something goes wrong and the actual car gets damaged, the robot spraying paint on, it's not a massive deal, so we're going to have to react continuously. I guess another point is that robots, they're going to be just repeating the same process basically, whereas a car, I guess it links in with unpredictability, but a car's going to be millions and millions of combinations, whereas a robot spraying paint is the same process. The final part I'm writing is the car has to analyse and react quickly, and this is probably all we need. If I'm going to write this up, I guess I should just emphasise that actually I always do a small plan for a longer mark question, you know, whether it's a 9 marker, 6 marker, a 25 marker. You won't get one of those in computer science, but I always do a little bit of a plan. Usually it revolves around a mind map. That's just my personal style, and I tend to just write a couple of notes jotted down. I wouldn't write it out like this necessarily. I'm just trying to show you my thought process as I think of these. So if we repeat this for the second point. So processing your inputs and why. So this is very much two distinct answers within one answer, two different subjects. It also talks about deriving information and the outputs too, but really I think we're probably going to focus on the inputs and also the why is the important bit. So first one we can maybe talk about is this video camera. And so the video camera is going to be picking up, I guess, extra objects. The radar is what's going to be picking up the cars surrounding it. You'd imagine that's pretty more accurate than a video camera, but a video camera will be picking up maybe potentially hazards that the radar wouldn't pick up, or maybe like signs on the side of the road, although that might be built into the navigation system, but maybe we can talk about it anyway. So, as I say, it's going to be analysed to identify significant objects. Analysing sort of still images coming from a video is going to be quite resource intensive, so really I think it's going to be used potentially for hazards, but I would reckon probably more road signs, because even if certain road signs are built in, as in the navigation road signs are built into the navigation system, things like temporary signs with roadworks still need to be picked up. So the second suggested input for the exam board I've got is the radar, and so this, I'm kind of imagining this a bit like sonar, but radar is going to be picking up the surrounding objects, so the 360 view of the cars in front, behind, cyclists, pedestrians, and etc. So it's going to be picking up the location of objects around it. And presumably it's going to need to track for changes of these objects too, if it's slowing down all of a sudden. And I need to start thinking about the processing, which I need to talk about in my actual answer. But it's going to be tracking the changes. So the processing that radar might have to do is to calculate the speed of nearby objects, which is going to be distance over time. So maybe actually the positioning will come from the GPS. So the GPS will tell us the exact, or pretty much the exact position of the car relative to the country or the road, and it will also tell us, so I guess things like if you're nearing a roundabout or a junction, and it will help the car analyse when it's going to turn. Also, GPS will probably also give us sort of an accurate, accurate time. I'm pretty sure GPS does that too. So it will be able to use the timing information to work out the speed as well. So this would be speed. Right, hopefully that'll be enough. I've got to be really careful of making sure I answer the question. So I'm going to do the same format as I did for the processor one and just type it up, and I'm going to show you my answer afterwards. So I've spent about maybe 8 or 9 minutes writing this up. This is probably about right a time. Obviously typing it up is easier than writing it with your handwriting, so give or take. When I at the end finish recording the whole paper, I'm going to sort of mark my answers. I won't show you all the marking, because if I get it right there's not much point telling you I get it right, but I'll actually mark this in more detail. So if you want to read it, pause it, but basically it's written up of what I've just planned, so I'll mark it and see how well it matches up against the mark scheme later. So if we move on, okay, we've got more space, I didn't realise that, to look at question 8. So a flight recorder is an electronic recording device placed in an aircraft for the purpose of facilitating the investigation of accidents. So the black box. Okay, so current cockpit voice recorders use solid state memory chips to store the digital audio data. Alternatively, it could be stored on a traditional hard disk drive. Give 2 reasons why they store data using solid state memories instead of a traditional hard disk drive. Right, okay, so I can think immediately of a couple of reasons why, or more than a couple. It says to give 2 reasons. So one reason is SSDs tend to be more durable than hard disk drives. SSDs are memory chips. So it's flash memory, and a hard disk drive is a spinning disk, and so it's mechanical, whereas this is not mechanical, and so mechanical parts are more likely to fail. So let's write that. So I've used a bit of a key term, which is reliability. This is how much you can kind of depend on the device not to fail, and because you have these mechanical parts, they're much more likely to fail than SSDs, and you don't want this really crucial bit of kit on the aircraft to fail, especially when it's going to be used after there's a collision. So second point might be talking about the fact that SSDs, so another point could be SSDs are smaller than hard disk drives, and I guess space on an airplane is quite important, but I'm going to say that SSDs are more robust than hard disk drives, so they're less likely to break. If you drop a hard disk drive, it's going to break pretty much, whereas an SSD is not likely to break, and I know this from experience. So if there's been a plane accident, you don't want your SSD, you don't want your data recorder to have broken. I mean, you might be able to recover data from a broken hard disk drive, but it's not ideal. So like I say, there are other reasons. So the space one I mentioned is also perhaps that SSDs tend to use a lot less power than hard disk drives use, so they're more efficient in that regard, and I guess that's quite important too. But we've got 2 marks there, hopefully. So next question is about so audio from a cockpit is sampled at a rate of 8,000 Hz and 16 bits allocated to each sample. How many kilobytes have been needed to store 360 seconds of audio? Show you're working. Okay. So if we just sort of talk about what this means, so if audio is sampled at a rate of 8,000 Hz, it means we're saving the amplitude of the audio 8,000 times per second. The unit Hertz just means per second, so 1 over seconds. And we're saying 16 bits allocated to each sample. And so what I tend to do, I've got a feeling there's a formula for this, but I honestly can't remember it. If I find it, I'll add it on in editing. But first thing, you don't have to use a formula. But what I'm going to do, I'm going to work out how much data is stored in 1 second of audio, and then we'll multiply it by 360. So for 1 second, there's going to be 8,000 samples per second, each using 16 bits. So it's going to be 8,000 multiplied by 16, and so this is going to be 128,000 bits stored per second in 1 second. And so if we try and convert this to kilobytes at this stage, so this is actually one of the things I looked up, because I looked up on the AQA specification, because different examples use different convention. The traditional convention and possibly incorrect convention is that there are 1,024 bytes in a kilobyte. That's kind of not true, because this is a decimal prefix, and a binary prefix is in terms of powers of 2, so it would be in terms of 1,024, but kilobytes are in terms of 1,000, so we're dealing with it in terms of 1,000 bytes. So I want to work out how many bits are in 1 kilobyte, and then I'll divide. So 1 kilobyte is going to have 1,000 bytes. This is 1,000 bytes, but there are 8 bits in a byte, and so we multiply this by 8, and so we're going to have 8,000 bits in 1 kilobyte. And so to work out how many kilobytes are in this, we're going to divide 128,000 by 8,000. We can cancel this, and this equals 16 kilobytes. So there are 16 kilobytes in 1 second of storage, and so this is for 1 second, 16 kilobytes, and so we literally multiply 16 by 360, which is up here, and the answer is 5,760 kilobytes. Right, our next question is asking us to explain why the highest audio frequency in the sampled audio from a cockpit cannot be greater than 4,000 Hz. Okay, so I can immediately recognise what this is asking us to talk about. It's asking us to talk about Nyquist's theorem, or the Nyquist theorem. And this is the theorem that states that the sample rate should be more than 2 times the highest audio frequency. So the sampling frequency and the audio frequency are two different things. This is the actual raw frequency of the audio, whereas the sampling frequency is how, it's our kind of defined sampling rate. And so Nyquist's theorem is saying that it should be 2 times the highest audio rate. So Nyquist's theorem is really something you just have to learn. It's just going to be part of your revision. And so really what it's saying is we need the sample rate to be greater than, ideally greater than 2 times the max frequency. And so the result is, if it's not 2 times, if it's so we're set with 8,000 hertz as our sampling rate. I missed a 0 there. Hertz as our sampling rate. We can't change that. And so if we get higher than this, this is not going to be greater than 2 times the highest audio frequency. So if we increase this, we're going to basically break this rule. And so the result is we get audio that isn't measured and represented correctly. I've written, so if the highest audio frequency is higher than 4,000 hertz, it may not be represented properly in binary. Really, it's just a rule for, Nyquist's theorem is just a rule for ensuring that the audio is going to be of a proper representation of the actual natural audio. Okay, next question is on Boolean algebra, it looks like. And actually, the first question is asking us to do something which we looked at earlier. It was yesterday for me, but early in the video we looked at the bitwise AND operation. And so we've got to complete the truth table for this. So the way you complete a truth table is you have 2 inputs for the AND gate. And so the first line you're going to write 0. So the way I think of it, you write it like 0, 1, 2, 3, and I'll explain this in a sec. So when you have an AND gate, 2 zeros, you need both inputs to be 1 to get a 1 in an AND gate, but I explained that earlier. And this is because AND can also be written as a dot, which is meaning to multiply, and so 1 times 1 is 1, 0 times 1 or 0 times 0 is 0, so this would not be an equal of 1. And so this is going to be 0, and then I'm going to write 1 in binary here, so that's 0 and 1, and this is also going to be 0. Then 2 is 1 and 0, also going to be 0, but 3 in binary is this, and this is going to be 1. And so basically what I mean with this is just a way to make sure you fill in all the combinations, and it works. Yeah, maybe you can see what I'm doing there. It doesn't really matter. So this is what a completed truth table looks like. To draw the AND gate symbol, the AND gate looks, I don't know how you describe it, I'll show you what it looks like. You have the 2 inputs coming in, and it looks like that. Not the greatest at drawing. It's meant to be like a straight line and a curve, like that. So this question is asking us to, using the laws of Boolean algebra, simplify the following Boolean expression. So what this is saying is, Boolean algebra is, I think the only way it's really tricky is you have to kind of think of it both in terms of normal mathematical algebra, but also bearing in mind that this is representing and an OR operation. So this is, a plus is representing an OR operation, and the dot, which is another word basically the same as a multiplying, is and. And so this is saying A and B are 2 inputs here, so A and B multiplied by A or B as the inputs. So what we asked to do is simplify it, and a lot of questions will be of this format, and so this will reduce to a simpler version. It's only worth 3 marks. And so what the first step I'm going to do is, like normal algebra, multiply out of a brackets. So this is going to be A dot B dot A, so A times B times A, by multiplying this, and then plus A dot B dot B. And immediately I can see one way we can reduce this. In fact, what I'm going to do, I'm going to rearrange this. So what I've done here, if you can see, I've literally just moved the A next to the B, and this is kind of a rule you're going to want to maybe bear in mind. So A dot B is the same as B dot A. The actual order doesn't matter. And so another rule is that A times A equals A. So A and A is A. And you know, to demonstrate this, let's do it up here. So if A was 0 and you had 0 and 0, it's going to equal 0, 0 and 0. It's going to equal 0. Same with both for 1s, as we can see from our truth table. This is and so we're going to get a 1. So it's going to be the same. And the same as with B. This is just a general example. So we can write this, go to red. We can write this as just A dot B plus A dot B. So we have this. And again, what I'm going to do is basic algebra, going back to just normal maths. And this is, I'm going to factorize this. You can factorize it in two ways. You could take out a B as a factor, you can take out an A as a factor. I'm just going to do A as a factor because it's first in the alphabet. So it's going to be A multiplied by the bracket of B plus B. And actually this is another rule too. B plus B, or any input, is equal to B. And let's prove this. So if B was 1, 1 or 1 is going to equal 1. If B was 0, 0 or 0 is going to equal 0. So it's the same. So we can collapse this finally, and this will be our final answer because you can't go any further. It's going to be, if it lets me, it's going to be A and B. I'm going to write it with a dot still to be consistent. So the final answer, simplified answer, is A dot B. Well, basically the same kind of idea, same thing to simplify it now. So again, I'm going to start by actually multiplying out. We're using two different inputs here. Sorry, two different letters to represent our inputs here. And actually this is worth saying is the not. This is representing not. So it's just the inverse. Or the complement of y. So I'm going to multiply these brackets out. I think it's called like a FOIL method. Don't know what that stands for, but what you do, you go x times x plus x not y plus y x plus y times not y. So this is us multiplying it out. And another rule is that it's the same rule as above actually, is this, so we can also collapse this, and so we can write this as x plus x not y, same as above, plus y times x. And actually I'm going to add another rule, and this is that an input multiplied by its inverse or not, this is going to equal, so let's say let's do A times not A, this is going to equal 0. And so in the same way that 0 in maths, you don't need to write it in, I'm just going to leave this off the end. So this is our next step, using both rules. So again, I'm going to factorize it. This is a sort of a general step. So I'm going to take x out. X is in every term, so it's going to be x, and our bracket's going to be 1, because 1 times x is x, plus not y plus y. And so for or, and so for plus, another rule is, so 1 plus anything, so we'll use the input A as an example, this equals 1. And that's because an OR only needs to have one input of 1 to be 1. So if A was 0, it would just be 1 plus 0, which also equals 1. And this is again kind of thinking of it in terms of the mathematical thing, because 1 plus 0 is going to equal 1. You don't even need to really think of the OR gate or the OR truth table. The only really difference is that if we had, so this is not any more to do with this, but if we had 1 plus 1 in Boolean algebra, this equals 1. So that's the only difference. So this can be written as, we can think of it like this. So we're going to rewrite this bit as x times, so this is replaced by 1, as we can see here. It doesn't matter, this is not y, so it's going to be 1 plus y, and you can see we've actually got the same thing repeated again, so this is also going to equal x times 1 now, because this is replaced by this, and so the answer is just x. because like in normal maths, anything multiplied by 1 is going to be x. Okay, final question, I think. Yes, it is. Okay, final question. We want to first, we've shown two versions of the same program, one in like a high level language and one in machine code or just binary. So the question is to shade in one lozenge to indicate which version A or B represents object code. Okay, so this is object code, not machine code. They are slightly different. So it's version B, and so really you're going from source code which is, to object code when you translate a program. So describe two differences between a compiler and an interpreter. The two types of translator. The translator does this process, and a compiler, what a compiler does, it translates the whole code, whereas an interpreter does it line by line. So that's our first point to make. So yeah, I've just written that the compiler translates the whole source code, whereas the interpreter does it line by line. So the compiler scans through the whole code, and which compares to the interpreter, which executes line by line. So sorry, translates line by line and then executes it. Second point is more of a comparison, and it's that the compiler object code executes faster than the interpreter object code. It executes faster because you have to. The compiled object code can just be executed, whereas if you want to then execute it again using the interpreter, it has to then translate every line again, which is why the compiled object code would execute faster on its own. So you get this executable file with a compiler. Okay, next question is, and final question, good news, is explaining what intermediate code is and why some compilers will produce it as the final output. So the way I think of intermediate code is like a high-level assembly language. So essentially it's kind of like a bridge in between the source code and the object code or machine code. So it exists in between the source code and object code, which is why I describe it as like a high-level assembly language, and it's essentially partially translated code. And this is done by most compilers nowadays because different machines have different instruction sets because the processor deals with instructions in different ways, and so the intermediate code can be general for all processors because it's not going to the specific level that they would execute at, so it can't be executed on its own intermediate code. It needs to be translated further. So almost you'd partially translate a program to the intermediate step, and then depending on what system you're using, you would use a different translator to then translate from this bit to the object code. And so it's kind of going halfway. So let me think about that and actually write it in a coherent answer. Hopefully I've written that better than I just explained it. So I've said that partially translated code so this is what I've defined intermediate code as, because we've got the and here, we've got to do both bits of it. So partially translated code that cannot be executed without further translation, that's our definition of what intermediate code is. Then why will it be produced by some compilers as the final output? Because different machines have different instruction sets, and so intermediate code can be general for all systems, and then the actual specific machines can then translate it fully to their individual instructions, and then it can be executed. So that's maybe a bit of overkill, but hopefully that'll give us for 2 marks. So I've just finished editing the video. I said in it that I was going to come back at the end and show you me marking my 9-mark answer, which I'm regretting a little bit now, but anyway. So the sort of general guidance in the mark scheme is that to get the top band, the top range of marks, is to have a line of reasoning that's produced a coherent, relevant, substantiated and logically structured response. And so to get in the running for the top marks, so either 7 up to 9 marks, you need to make at least 2 points from table 1, which is about the car versus how easy it would be to program a robot, and also you need to refer to 3 sources of input from the other table, which is about the actual specific processing and inputs. So I'll show you me kind of marking mine to an extent. Obviously it's kind of subjective, and examiners will be trained by AQA to do stuff to mark questions like this. So from the first table, let's see how many I got. Hopefully I've got at least 2. So I've said First point is, by the way, it doesn't seem like you get marks for definitions. I did a definition here. In some essay situations you do get a mark for definition, but obviously not in this case. It's maybe worth doing anyway, but don't spend too much time on it in case you don't get a mark. So what I've said is, the first point is that the automated car is in a very unpredictable environment, and straight away I can see that it says the environment for car operators is not predictable, so that's good to know that I've got at least 1 point from that. Second point I talked about was the production sequence being systematic and continually repeating. So yeah, exactly the same operation performed over and over by robot sprayer. So that's good. So we've got two points there. Where is it? There we are. So we're in the running for the top marks, which is good. And so we need to look at the next table. Then we need 3 sort of bits matching up in terms of the inputs. And so the first one I kind of talk about is the digital camera. And so it needs to analyse each frame for significant objects. So this is a radar. I still don't really understand what a stereoscopic camera is. So high resolution video camera. So frames processed. I think I said analysed and matched by comparison with a database of road signs. Okay, so I talked about road signs, so that's good. And then for Y is about highway code and junctions. So okay, I did say highway code. That's good. And I said analysing each frame. That's basically the same thing as processing. So that's, I'm going to count that as one bit. The next part will be I talk about radars determining location of objects. So we go up to look for radar. Obtain location information. That's kind of the same thing. And so I talked about tracking. So that's changes in position. Okay, so yeah, I'm going to count that as another point. I do think so far I definitely could. You can see they have loads of specific reasons. Radar. Yeah, so location. So there's loads of very specific reasons here. I can't imagine many people would get some. You know, some of them which would be, you kind of have to be an expert in this field to get, perhaps. And I definitely didn't get close to some of them. It looks like the GPS is. I've talked about locations. Then this is my processing bit. So yep, location information, precise location. That's kind of what I meant. And then to determine the speed of other objects or speed of car. I'm going to give myself that. I think that's my weakest of all the points. Actually, it does seem like I haven't. If I could improve this, which I definitely could, is go into more detail about the derived information and perhaps how you get there, and also why. I haven't really gone into massive amount of detail about why. So I don't know, it's arguable if I'd get 4 marks for this question. Maybe 8 is probably a fair mark. And generally for the rest of the paper, I'd say I probably wouldn't have got 4 marks. In the video I added an annotation for the character code one where my definition was a bit relaxed. So if I was being a harsh marker, I wouldn't have given myself a mark there. So I got pretty close to 4 marks. I'm relatively happy with it. It'd be difficult to get 4 marks unless you knew the answers, which I was thinking halfway through me recording it, that actually it would be probably a better format if I did know the answers beforehand. I just showed you how you get to them and then did a bit of revision of the topics. I did a little bit of revision of the topics, but it was all kind of off the top of my head, so it wasn't as solid as it could have been. So let me know if this has been helpful. If there are any improvements, let me know. If there are additional questions on the website, there's not a full paper, I don't think, for paper 2. I can't really do paper 1 because it's programming, but I can maybe get some questions from other exam boards, like the old AQA computing course perhaps, and answer those. So let me know what would be useful. I can't cover a whole course like I've done on my channel for GCSE courses, but maybe I could do some revision videos. So let me know if there's any topics that you think a lot of people will be struggling with or you're going to forget easily. So yeah, thank you for watching.